Hello, this is a video about shortest distance, and we're going to start by talking about in 2 dimensions and a bit of review of grade 10, and then we'll move on to 3 dimensions where we have to utilize vectors. So this question asks you to find a distance from point Q, which is over here, to the line that's already pre-drawn for you. We're going to first of all do this as a grade 10 student, as a quick reminder, and you'll see how many steps it actually takes to do this. So if you were at point Q and the blue line was a wall, for you to walk at shortest distance towards that wall, you'd go at it straight at 90-degree angle. So let's call this point where this line, perpendicular line, meets the blue line, point R. So our goal is to find this distance between point Q and R, but the problem is we don't have the coordinates of point R, and I don't want you to just estimate and say it's 2 point something and close to like 6 up, because we want to find precise coordinates of this point R. So to do this, we need to find the point R, which is going to be the point of intersection of the blue line and the green line. Well, the blue line is given, so if you were to reorganize it and get y isolated, you'd have this relationship. And to find the green line, we need to do some steps. So first of all, slope of the blue line is -7/1, which we could see in this slope point or slope y-intercept form. And the green line, because it's at 90 degrees, we could do negative reciprocal of -7/1 and we'll get +1/7. Then to find the equation of a line, you could use slope point form or slope y-intercept form. I prefer to use this one because then the variables will be already present. I would not have to rewrite it. So I'm going to plug in a point that I know that's on this green line, which is only point Q. So when you do that, you'd have y minus 8 is equal to our slope 1/7 x minus 5. And the reason why we have negative here, we're just following the formula. And if you isolate the y and distribute, you would get this version. So we're going to take this result. We're not finished yet. We just found the equation of the green line. We're going to put it over here for reference. Our next step is to find this POY. So because this is y equals and this is y equals, we can make them equal to each other to solve for x. Now, I don't like working with fractions, so we're going to multiply everything by 7 to get this result. Then we can collect all x's to one side and everything without an x, all the constants to the other, and solve for x this way. And then, as usual, you plug in your found value for x into any one of the equations to find the y. I chose to use the blue line to find the y. Now, this is our point R, so I'm going to put it here for reference, and I have the fraction version, also the decimal version if you prefer to work in decimals. I prefer fractions because then it's very easy to tell that there was no rounding occurring. The 2.2 is not very easy to tell whether this has been a rounded answer or not. And all that's left was to plug point Q, which is provided 5, 8, and the point R that we found into the distance formula, and you would get your result of roughly 2.8 units. So now let's redo this question, but we'll use vector projection, which then will extend into 3 dimensions. So what we're going to do is we'll find any point R on the line. And it doesn't have to be point R that we had at shortest distance before. It could be any point on the line. So I'm going to just randomly choose x equals 1. So if I plug in x equals 1 into the given equation, I can solve for the y that's corresponding to it, which is 16. After you have found a random point R, which is easy to do, what you want to do next is find the vector between 2 known points. So the point you just found and the point that's provided. So let's call this vector RQ because that's the way I oriented my arrow. In order to find RQ vector, displacement vector, we want to go through the origin. Why the origin? Because the position vector that's pointing at point Q has to have its tail at the origin. And when it does that, then we can quote 5, 8. Instead of it being coordinates of a point, they now become components of this vector that's pointing from the origin to point Q. And so RO could be switched to be negative OR, so that then we could use the point 116 as the components of vector OR. After the subtraction, you have vector RQ. So shortest distance is going to be a scalar projection of vector RQ onto the normal of the line. And let me explain a little bit of what's happening here. So first of all, I had a mistake here, I had P, so it's RQ and not PQ. This line right here is a magnitude symbol. And they're the same symbols that we use for absolute values. All it means is to ignore any direction that we get out of this vector projection, meaning that we're going to get just a number, which makes sense for this to be a distance, which is just numeric. So we're going to be projecting our Q onto N, and N is going to be the normal of the line. Normal just means perpendicular to the line. So we have learned in this unit that the normal could be gathered from the Cartesian equation of the line. So the A and the B here would be the 7 and the 1, the coefficients of X and Y. So if you were to actually go 7 to the right and up 1, this would be the vector N, which you could kind of tell that it's not exactly at 90 degrees to this, because my scale horizontally, notice how 1 unit here is way longer than 1 unit vertically, just the way I drew it. So it looks a little bit warped, but let's assume this is at 90 degrees, and I just move this normal vector to the point R, so I can explain this projection for you. So you've learned in this unit that if you were to project vector RQ, so this red one, onto the floor, which is this purple normal vector, then what you're thinking of is the shadow of this vector up onto this the purple vector, which is going to be represented by this yellow region that I've highlighted. This yellow region that I highlighted is actually exactly the same size as the distance from Q to this line that we're looking for. So that's why this scalar projection will be the shortest distance that we're looking for. And here we have a reminder of the formula of the scalar projection. Another note here about these magnitude symbols or absolute value symbols. So because on the bottom we actually get a vector, so the lines or bars here, they mean to ignore the direction. But as you know, that dot product yields a number, so these lines here are to indicate that if this number happens to be negative, you're going to ignore the negative. So on the top, we're ignoring negative. On the bottom, it means to find the magnitude of a vector. And so you could pause at any time to look more closely at my calculations. I'll go a little bit fast here. So when you get to this point right here, you cannot reduce these numbers if both of them are not under the root. So what I have done is I square 20, but also put a square root on it, so they don't actually, they cancel each other out. So this is still equivalent to 20. But now that we have done that, it will have 400 over 50. So you could reduce these numbers now because both of them are under the root. So you could leave it as root 8. Some of you have not learned yet how to get to this version, so just go straight to the decimal. I'm okay with that. All right, so as we have learned here, we have a scalar projection of a random point, which is very easy to do, to find, find the vector to the given point and project that onto the normal. Question is, would that work in 3 dimensions? That's our next question. So we have in 3 dimensions point Q, and we have a line here provided in vector format. So I'm going to call this position vector OP, so that means there's a point P that's on the line, and I'm going to call this direction vector M, kind of like indicating the slope of this line. So our discussion right now, will what we've done before work here? So here's normal. Here's also a normal. So as you could tell, there's so many different normals for a line in 3D because this normal can swivel around this line. So there is no unique normal, so this formula goes out the door. This formula will be useful when we're doing a point to a shortest distance to a plane. But because there's infinitely many normals, this formula is not possible to be done. So projection does not work. So what we're going to do is another concept we learned in this unit. If you recall area of parallelogram, we're going to utilize this concept right now. So let's start by, first of all, finding vector PQ. So we have a point here and a Q, so that's easy to find PQ. I'm not going to go through in detail how we did that again, because it's similar to before. Then I'd like you to utilize the direction vector M that's provided and the vector PQ that we found to create a parallelogram. The height of this parallelogram will be the shortest distance that we're looking for. So, quick reminder, area of parallelogram is base times height. But we also learned in this unit that it could be found by taking the magnitude of the cross product between the two vectors that create this parallelogram. So this parallelogram is created by vector M and this PQ, and so all we have to do is find the cross product and then find its magnitude. However, we're looking for only height. So if we were to isolate for height, base of this parallelogram will be the size of this red vector, which is the size of magnitude vector M. So in the end, it ends up to being this formula, which is very similar to what we had before, except before we had a dot product and we had normals here and here. So on the side here, I have my computation of a cross product. There's different ways that people do cross products. I've learned it this way and I'm more comfortable doing it this way. So let me quickly recap how I do it. So what we're going to do is, I actually did PQ cross M, but my formula has M cross PQ because we're going to be taking magnitude of this cross product. It doesn't really matter the order how you do this. Usually the order of the vectors that you do cross product with do matter, but because it's going to be just the size of it, then don't worry about that. So what I do, I take my first vector that I'm going to be cross product with, so I put the components 2 times. Without the commas. Then I take the second vector that I'm working with, and again, I put it down 2 times underneath, without the commas. Then I ignore the first column and the last column. Then, to find the first component of the cross product, I'm going to multiply 0 times 2. That gives me 0. And then I'm going to subtract 0 times 1. So that's still 0. Then you repeat for the y component, 0 times 1, which is 0, and then subtract 2 times negative 2. So that gives a double negative, so that's a plus 4. And then z component similarly, negative 2 times 1, which is negative 2, and subtract 1 times 0, which is 0. So this is my cross product. And what you want to do is find the magnitude of this vector. So always pay attention to the context for these bars, or whether it's a magnitude symbol or absolute value symbol. So what's inside is a vector, that means we're doing magnitude. If what's inside was a number, then you just ignore the negative on that scalar, okay? So we have on the top, we need to find magnitude. On the bottom, for our M vector, which is 1, 1, 2 provided, we need to find that magnitude. And the result in the end ends up being 1.8. For this particular question. We're going to do this question in a different method another day or another video, so I'll refer to this 1.8 I think a little bit later, just for comparison's sake. Our next situation to discuss is if we have a point, we want to find the shortest distance from that point to a plane in 3D now. And so because there is going to be a unique normal, what we've done before will actually work. Before we do that, quick discussion. When we have a vector equation of a plane, you have to truly check every single time you're given that if it's a true plane, because if these two direction vectors were multiples of each other, then it's one of them would have been redundant and it's actually going to be just a line. So what I'm going to do is I want to find the normal of this plane. So I'm going to take direction vector m1 and m2, and I'm going to do cross product on them. So you could pause and double check my work, but I'm not going to go through in detail how to do that anymore. And so I'm going to draw this normal vector in here on my picture. Then let's name this position vector that's pointing at a point on the plane. Let's call it point P. And so it doesn't have to be this particular point. You could find any point on the plane, but let's just use the one that's provided here. Then what we want to do is find the vector PR. Okay, so from any random point that we have to the point in question that we want to find the shortest distance from. So as usual, we go through the origin, we find this displacement vector, and you could pause to take a look at the steps there. And so the shortest distance is again going to be the scalar projection of PR onto the normal. So let's explain the scalar projection again. So let's move the normal vector to be at the tail of the vector that we're projecting PR onto this end. So think of the N as being the floor. So I just extend this line, and what you want to do is find the shadow of the black vector PR onto that floor at 90 degrees. So it's going to be this size right here, which ends up being the same size as the shortest distance from point R to the plane itself. So here's the reminder of the formula again, and you could pause to look at the calculations one more time, and the answer for this is 8.3. And again, this is one of the questions I will come back to in another video to do in a different way. Here's a summary of what we've done. This can be found in your notes. So the two that are similar are the shortest distance to a line in 2 dimensions, as well as the shortest distance of to a plane, but this middle one is a little bit different. I do find that I prefer the other method that I'm going to show you in a different video, due to the fact that that method works no matter what you have, and there's going to be less to remember with that method. It also gives you the point at shortest distance, not just the shortest distance itself. All right, so that's it for this video.